So now this video is going to teach you how we are going to use table 3-10 and 3-11 for the steel beam design. Let's grab the manual and go to page 3-119. So now on this page you can see there's a lot of lines with some dashed line, and you can see we had a different section, different height, different weight. Some are dashed, some are solid. We had solid dots, we had hollowed dots. And then what are they? How we are going to use it? So basically the solid dots here means if you try to read down to here, that's actually the LP. And then for the hollowed dots, if you read down here, that's actually LR. So if you recall the diagram we had been talking about, this is the LP and LR. That's actually in our design manual. And the second question probably you are going to have is why some of them are dashed line, some of them are solid line. This is because, so for example, if you try to design a 4-foot beam and then you try to read it, whenever you hit the first solid line, that's actually the most lightest weight you are going to have. The dashed line here means it might be not as light as the solid one here. So which means in our class, we're always going to try to find out the solid line because that's going to be the most economical section you are going to find from the manual. And now let's take a look at here. Let's go up. Let's try to find out this W1253. And you can see we start with some dashed line and then dashed line back here. And if you keep reading underneath the page here, you can see it actually becomes to the solid line, which means if you design for the longer distance, it might becomes to the lightest one. And then if we try to flip to the other page, and then we had a different section, and you actually kind of lost. Can you find the W1253 from another page? You also get lost, right? So how we are going to find out the W1253? So here is the tricks. So you go to here, and then you see, okay, it's around 18 feet, and then it's around 240, and it disappeared. So which means what you can do is go to the next page. We still find 18, and then we go up to 240. We don't find it. And then we go to another page. We're still at the 18 feet. Try to read, 240 here. And then you can see you still not find it. It's 1453, not 1253. So which means this is not the right page. And now let's go to page 3-122, and then we had 18. Did you see that? And let's try to find out 240 where you lost the W1253, and then you can see it's actually here. And remember, when we disappeared, it's actually a solid line. So it will be a solid line, continue until it was finished. So did you see 1253 here? And then you keep going. And then we can actually draw this curve continuously from 28, between 28 and 30, and then it disappeared around 120. So which means what we are going to go is go to page 124, and then we can find the W1253 again, which is here. Did you see that? So this is actually just to tell you this curve here is actually too big. So you can see just for this section, it's actually been breaking down to 3 different pages. And that's what we are reading on the page 3-119. And then I showed you how to trace down to find this section again. And then the last elastic deformation is here. So basically, this is too big. So that's why we cannot finish just for 1 page. That's why we have to go to different page to find out our sections. However, whenever you are using this table here, you can see it starts with the dashed line, which means it's not the most economical one, but it might be in the future work, right? So what you need to do is always remember in this chart, if you try to read, the vertical line here is actually phi mm. So which means we don't need to multiply the reduction factor 0.9 if you are directly read from this table. Don't double count. And then second of all, we can see this is actually where we got lost our section 18 feet, and we finally kind of find it here. And the horizontal axis is going to be the unbraced length. So basically, this is a very big chart. And we had different parts at different pages. And then, as I mentioned, it's going to be always phi mm for all. Yeah. So now, let's take a look at here. The property of this table, as I mentioned before. So the solid dots and the hollow dots. And then the solid line is going to be the lightest section with the given unbraced length and your load. So now the steps to design a check your steel beam design. So first of all, the first step is try to calculate what is the real CB and unbraced length. And then what we are going to do is try to calculate this. Why? Because remember, in the chart, the CB value is always going to be 1. And then what we need to remember, when you calculate ultimate moment here, don't forget about the self-weight. After all the calculation, what you need to do is try to read along the LP, like I showed you, and then go upwards until our phi mm is going to be bigger than the requirement. And then in our class, remember, we always try to find out the solid line for the lightest section. And after this, we done all the beam design for the flexural. Eventually, what we are going to do, we have to check the other requirements, like the shear and the deflection in the future. And I will show you how. But basically, this is what we are going to do. find the length and then go up, read this. And you have to be very careful. The scale on each load is different. You can see this. We had 1, 2, 3, 4 grades to the 66, which means every grade here is 6/4, 1.5 increment. However, let's take a look at here. From 465 to 480, it's 1, 2, 3, 4, 5 little grade, and the whole increment is actually 15. So which means every grade here will be 3. So you have to watch for that. It's not uniformly for all the tables. And then, like I mentioned before, this column here is always going to be phi mm.